Welcome to Walkabout the Galaxy, the unstoppable astronomy podcast where the science is universal, the opinions are personal, and the trivia is topical.
Topical?
See what I did there?
No.
You didn't?
Oh, I do. I do now.
Okay.
Because I'm giving it.
That's
and
right.
I'm the top quark. I get it.
There you go. We are Strange, Charm, and Top the Astro Quarks, also known as Josh Caldwell, Addie Dove, and Jim Cooney, coming to you from the Walkabout Studios at the University of Central Florida. But today, we are charmless. Addie Dove is on assignment at NASA's Exploration Science Forum, leaving me and Jim behind to fend for ourselves, and we fended by asking Anna Turner, longtime Walkabout listener and instructional specialist at UCF, to join us, who brings plenty of charm herself. Welcome, Anna.
Thank you, Josh.
Welcome to the Walkabout Studios.
I'm very excited to be here. It's super high tech.
Not in the usual studio sense, though. More in the nerdy professor sense.
Right.
Anna, we usually start things off with a challenging decision or choice for Jim and Addie, and I'll start with Jim so you can see how it's done. Okay.
Mm-hmm.
Jim, you ready?
I'm ready.
Ryugu'd or Bennu?
So these are the two targets of our two sample return missions. I say humanities.
It sounded like I was having a stroke.
It did.
But actually, I did say what I meant to say.
It did. Yeah. And I got it.
Ryugu'd. Which is just fun to say. Ryugu'd.
It is.
Or Bennu.
Yeah. When your only vowels are U's and maybe a Y, that's a pretty awesome word.
Yeah.
Ryugu'd is the target for Hayabusa 2, which is a mission.
Not a Scrabbleable
Definitely
word.
not a good Scrabble word.
Okay.
And Bennu was the target of
OSIRIS-REx,
the NASA sample return mission. I think I'm gonna go with Ryugu'd
because it's more fun to say.
Because it's more fun to say, and we have pictures of it, and we don't have
already.
Pictures of Bennu.
Well, just dots.
Yeah.
Bennu's just a dot.
Bennu's just a dot because we're still quite far away from it. Whereas Hayabusa 2 is closing in on Ryugu'd, which is of course one of the topics for today.
Right. Okay. Anna.
Yes.
You got the idea.
I have.
Okay.
I think I've got it. I wish I
Okay.
had gotten the OSIRIS-REx one though, because I actually crashed a party at one of the investigators' retirement parties for that.
Really?
We didn't know we were crashing it, but yeah, we were.
What did you think you were doing?
Well, we thought we were going to like a celebration party, and it turned out to be a retirement party in a timeshare. And so, we stayed under the radar for a little bit.
I mean, a retirement party kind of is a celebration, isn't it?
Well, yeah, yes, but we thought it was just like a mission celebration type of thing. We didn't know there was an underlying, hey, this important investigator is retiring.
Oh,
thing.
Okay. This was not a UCF person? This
No,
was a
it wasn't.
mission
I think it was an ASU person.
Yeah,
No.
Arizona State.
Mm-hmm.
Okay. Well, your choice does have a thematic connection in some way to our previous choice. Kyoto or Bento.
That's difficult.
Not asteroids.
Yeah.
I mean, there's a definite Japanese theme going on there. Bento makes me think about food, though. I'm a big fan of food.
Yeah. Kyoto doesn't make you think about food?
It does because of the restaurant, but
Yeah.
bento boxes are so nice and neat. But I think I'm going to go Kyoto.
Okay. Why is that?
I just was drawn to it.
Okay.
And because I feel like I'm making the wrong choice by going with my stomach.
Okay. To me, they're both stomach choices because there's both a Kyoto fast service Japanese restaurant and a bento fast service Japanese restaurant within a very short distance of the Walkabout Studios. And they're both frequent lunch destinations for me.
It was probably a subconscious choice with me, too.
Yeah. Yeah.
Delicious.
So Kyoto and bento, Japanese things. Ryugu'd, Japanese.
What is
Bennu?
What is Bennu?
Where does that come from? We may have discussed that before, but I have no memory of what the answer was.
I don't know.
Bummer.
Anna, do you know what
Where
Bennu is?
I do not.
Okay.
Wah, wah.
We'll post it. Yeah. Or not. I'll probably forget to post it. Bennu is the asteroid that OSIRIS-REx is going to. That's what it is.
It is, but it's the name comes from something.
From somewhere.
I don't know where it comes from, though.
Well, does it look like it? Well, we could speculate without having any knowledge about it. And that
Well, we never do that, Josh.
Yeah, but we'll do that.
I mean, that's an important aspect of science.
Speculating in a complete
Yes,
absence
yeah.
of data or information or knowledge of the subject.
Yeah.
Right. Yeah. Well, speaking of Ryugu'd, that will be one of our topics today because the Hayabusa 2 mission, which is a Japanese aerospace agency. JAXA is the acronym it goes by. I don't know exactly how that spells out, but it's the Japanese NASA, JAXA. Their mission, Hayabusa 2, has essentially rendezvoused with Ryugu'd this week-ish.
Right.
It's so small. Like with Cassini, when Cassini got to Saturn, there were Saturn orbit insertions. It's really dramatic, like hour and a half or 2 hours, where it's burned 3,000 kilograms of fuel to slow down enough so that Saturn's gravity could capture it.
Right.
I talk a lot about Cassini, Anna, by the way. Just to brace yourself for that. But you already know.
I've learned a lot about Saturn. Yeah. Did not know those rings were so young.
Yeah. Well, we didn't either until very recently.
It's very exciting.
The other thing we talk a lot about is Boulder, Colorado. And you know something about Boulder, Colorado. Tell us.
I've only ever been there for a day and a half, but I am moving to Boulder, Colorado toward the end of August to finally pursue my PhD at the University of Colorado Boulder.
Awesome.
Which I hear is your alma mater.
It is. And Addie Dove's as well.
Fantastic. Yeah. Congratulations.
Do you think Carl Wyman does selfies?
Carl Wyman's no longer there.
I thought he was still there half and half time, doing some learning science stuff.
Well,
who is this?
Carl Wyman is one of the recipients of the Physics Nobel Prize, Jim, so you should know that.
Yes.
For
what?
The Bose-Einstein condensate.
Oh my gosh.
Yeah.
How did I not know that?
I don't know.
He
and Eric Cornell and somebody from MIT, I believe, shared that in the early 2000s for the Bose-Einstein condensate, which was made for the first time ever just around the corner from my office. But I was completely oblivious, of course, to all that excitement. But he went to British Columbia and then Stanford.
Yeah, I think he's now doing half and half time because he's doing learning science stuff.
Right.
So
he studied, and that's your area. So you're help us be better teachers. You help people like me and Jim not suck so much in the classroom.
Good luck with that.
True. Yeah. And use evidence-based practices rather than just, making assumptions based on not any data.
Oh. Well, I don't know anything about that.
Yeah, it's really weird.
That's crazy. So we'll talk about, I was saying, unlike Cassini's arrival at Saturn, before I multiple tangented myself there, this spacecraft's getting to this little tiny asteroid whose gravity is so small that the, arrival, it's hard to sort of put a time and say, okay, now we're there. It's just sort of gradually getting closer. It's really quite close to the asteroid already. There are some amazing pictures of it already. It's a very funny sort of diamond-shaped or top-shaped asteroid. So it's basically there. It's going to hang out there for a while. We'll talk about that. We'll also talk about the James Webb Space Telescope and some of the cool science it's going to do. But first, this episode of Walkabout the Galaxy is brought to you by the sun.
Oh!
What's the source of 99.975% of the energy reaching the surface of the Earth? A young-looking 4.6 billion years old and weighing it at a svelte 300,000 plus times the mass of the Earth, your hometown star, Sol. The source of virtually all life-sustaining energy on the homeworld is giving up mass at a rate of 400 million metric tons per second just to brighten your day. Eat that energy up because you're wasting most of it and I ain't got an unlimited supply. 5 billion years, give or take, and I'm checking out, and I plan on getting hotter before then. So you take a cue from Walkabout the Galaxy and learn how to walk about the galaxy before I make your home a bit too toasty. You can call me Sol, and I'll be sure to rise. The sun, keeping things together so you can do all the things you need to do, is proud to sponsor this episode of Walkabout the Galaxy.
Oh, thanks, Sun. Sun is very wealthy. So that is excellent.
The sun is got everything, all the mass and all the energy, but not. There's one thing that it doesn't have most of in the solar system.
What?
Yeah, it's got most of the mass, most of the energy. Mm-hmm. It's at the center of things. It's got the biggest magnetic field. The most plasma.
Not angular momentum?
Angular momentum.
Yes.
Yeah. It doesn't have most of the angular momentum in the solar system. That's a fun fact.
Yeah.
It's a fun fact for me and Jim. I don't know how fun it is. Inez, do you find that a fun fact?
It's definitely a fun fact for me, but what does have the most then?
Angular momentum?
Yes.
That's an excellent question.
Yes.
Jim knows.
I know.
Yeah?
Yeah.
Take a guess, Anna. Something else in the solar system has more angular momentum than the sun. We're picking on our guest.
Oh my gosh, already? I feel like,
As long as you name something in the solar system, I'm going to give you props.
I mean, I've got planets and not so planets and other stars. Right. And is it another star? Is it a different type of body?
We don't have any other stars in the solar system. So the solar system's the sun is the only star in this solar system, in this system. A lot of systems have two stars. Those other stars are doing their own thing.
Yep.
I don't know.
So you can take a crack at it. Angular momentum has to do with...
Is it a planet?
It is.
Is it a big or a small planet?
Well, angular momentum is proportional to mass.
Okay, so... But that's mass. That's not, like...
Yeah, but go with your gut.
The ones that are bigger.
Go with your gut.
Are more massive.
I think you're there.
Like Jupiter?
You got it.
There you go. Yes.
Oh
Excellent.
my gosh.
See? Astrophysics is
I feel like
easy.
I forgot all of the basics just sitting here with you guys.
That's awesome.
It's tough when you're put on
on the spot.
On the spot.
Pulled it off. That's great. Yeah. So tell us a little bit about what you're going to be studying when you go off to Colorado.
Sure. So my PhD is going to be in media research and practice. So my focus is on
podcasts.
Maybe
promoting podcasts.
Astronomy podcasts.
Mostly it's political stuff. So I look at how political media affects people. So my previous research has been done.
Makes them dumb, I think.
Yeah, well, that is sure.
You must have a thick skin and a tough stomach to do that.
It does.
This
I
day and
mean, you
age.
find out great things in the media, like NASA just reopened. So that was an exciting thing that I found out from the media the other day. But mostly how it affects people and how we come to either mostly like re-solidify our beliefs type of thing.
Yeah.
So my outside, you have to have an outside area. It's really interdisciplinary. So I'm hoping that my outside area can be in cognitive science because they've got like 11 really great cog-sci labs.
That's the science of understanding gears.
Gears in the brain, I guess.
Okay.
You could move it that way. And so to see kind of how the different ways we react to media and how we learn from that. So that's my area of interest. And then space is just kind of a fun hobby. Clearly not an expert on that.
You got the question right. So that's better than we do half the time.
Yeah. Better than most of my astronomy.
Then your
101
trivia
students.
question answers too.
That's true. Yeah. I routinely
get
those wrong.
It's
tables.
harder when you go first.
It is.
Yeah, that's true. Mm-hmm. But you did go first today.
Yeah. It was also not numerical.
That's true. That's true. Yeah, I mean, speaking about, cognitive science, it's one of the things that we've talked about sometimes, and we face it all the time as teachers. And of course, not to pretend that we're immune to this particular phenomena of the human brain. It's very hard to change your opinion about something. Mm-hmm. So you think you know something, and even when presented with evidence that it's the other way around, frequently what people do is they just dig in their heels and double down on their wrong ideas. And I say I'm including all of us.
Sure.
I have a fun fact about that.
Oh, cool.
So, prior knowledge is something that we study in the learning sciences a lot because of that phenomena that you're talking about. And actually, when we observe over like meta-analyses that have been done, we observe that prior knowledge can actually account for 30 to 60% of the variance in student performance. So it's not necessarily that students are bad students or don't want to learn the material, but things that they have learned before they got to class can affect how they learn the materials as one of the major factors. So.
Right.
It's a fun thing.
And in physics, this is a big, and astronomy too. I mean, tell some hilarious stories about misconceptions in astronomy, and I can tell some about physics. I mean, for example, the seasons.
Yes.
Yeah. So actually, today I teaching summer class, and today I asked a question to the class. Basically, what is the cause of the seasons? And had several choices, a multiple choice thing, and I want to say 85% of the class chose the thing that was, the summer is caused because your side of the earth is tilted towards the sun and is thus closer to the sun, right? This is the common thing, right? So,
right.
And it's hard to beat out of. And then, of course, I went on and explained the real reason for the seasons after that, but
they don't believe you.
They don't believe me.
Right. And even if they get it right on the final, it'll only be because they know that they need to put that obviously stupid answer down in order to get the points on the final.
That's right.
There's an interesting documentary you can find on PBS called A Private Universe, in which they follow a group of late elementary, early middle school kids about looking specifically at that misconception of the seasons, and also about the phases of the moon.
Yeah.
And so they look at that. It's really
and of course,
interesting.
this one is a difficult one because if you are closer to the sun, you will be warmer.
That's right.
Right.
That's right.
It's just not what is actually going on
right. Yes,
here.
right. And a lot of this misconception is based in a total lack of comprehension of scales, right? So this is something that we really work hard in an astronomy class to teach, is an understanding of how much larger, like, the distance between Earth and Sun is compared to the size of the Earth, or,
And how do you even get somebody to think about in that? Because those sizes are so massive.
It's very challenging. So I do all kinds of fun things, like show these cool videos, where you, like, change your perspective by powers of 10 over and over and over again. But still, you can't just lecture to somebody about that and then they're like, oh, okay, now I understand it. You have to,
it has to be
internalized.
Repeated.
Yeah.
And, so I'm been crusading incredibly ineffectively for a scale model solar system on the UCF campus.
Oh, yeah.
Oh, cool.
I remember you being on about that 10 years ago.
Yes.
What happened to that? I haven't even...
Well, I've been off being incredibly ineffective. So a campus like UCF is about the right size to take the solar system and shrink it by a factor of 10 billion. 10 to the 10. If you shrink the solar system and everything in it by a factor of 10 billion, the sun becomes something about the size of a grapefruit. Wow. Okay. And the Earth becomes the size of the ball and the tip of a ballpoint pen. Mm-hmm. And it's about 15 meters away, 15 long strides away from that grapefruit. And Pluto is then about 600 or 700 or 800 meters away from the sun. Mm-hmm. So the full diameter of the solar system is about a mile. In that, if we go out to Pluto as a sort of arbitrary edge for the solar system, Jupiter, the largest planet, the one with all the angular momentum, is about the size of a marble, and it would be about 60 meters away from the sun. So, if you think about this question about the seasons and whether or not you're closer to the sun, think about being on the ball of a ballpoint pen, 15 large strides away from a grapefruit. Doesn't make any difference which side of that ball you're on. Right. And what matters is whether you're tilted towards it and the sunlight's hitting you directly. Face the same thing with Newton's laws. We teach physics as well, and people are just sure that the truck exerts a greater force on the bug than the bug exerts on the truck when they hit. Right. And it's impossible. I spend literally, it's not really an exaggeration to say my entire goal in teaching Physics 1 is to overcome that preconception.
Very challenging.
For students, it's very difficult. Yeah. So I'm glad you're studying it. And when you figure out how to solve that problem,
just let us know.
Come back and let us know, and we'll do the right thing.
Great. I'll see you in a couple weeks.
Okay. Awesome. That's awesome. So Hayabusa 2 is this Japanese mission. It's essentially arrived at Ryugu'd.
You say it right. So is it? It's very difficult to orbit a thing like Ryugu'd.
Yeah.
Because it's so light. So is it going to orbit or just like parking nearby and occasionally correcting itself so that it doesn't wander off?
It's orbiting in the sense that it's going to be surveying it and taking pictures of it from a number of different vantage points, but it's not orbiting in the sense that it'll truly be, I think, gravitationally bound.
Okay.
But I'm not. It's certainly possible for it to become gravitationally bound. I mean, a lot of asteroids we've talked about in previous trivia, have moons.
Right.
So even a tiny moon like Ryugu'd could have a moon, and that moon could be the Hayabusa 2 spacecraft if you did things the right way.
Right.
But operationally, they're going to be firing their thrusters to put themselves in the right position. It's a very cool mission. It's got rovers. It's got an impactor. They're going to shoot down onto the asteroid to make a crater, and then they're going to go get a sample from that crater and then bring that back to the Earth. So it's a pretty ambitious mission.
Very ambitious mission. I was really surprised to hear about all the different things that they've kind of packed onto this.
Yeah.
Like sample return just in
By
and of itself
itself
is already hard, and yet they've also got all these other attached things.
Right. So you may have noticed the 2 in the name Hayabusa 2.
I did notice that.
Yes. Because Hayabusa, numberless Hayabusa, has already done the meet up with an asteroid and bring something back.
Right. Kind of. So that was the mission. And it depends on who you ask whether they were successful or not.
Yeah, it was a partial
success. It didn't do exactly what it was meant to do. So it was meant to go down and kind of get very close to the surface, grab some, basically I think like shoot a big puff of air or something like that and grab a bunch of stuff, something like that. It didn't work the way it was designed to work, but it did end up grabbing. They did open the collector and close it back up, and it did end up grabbing a handful of grains of stuff from this.
It's a fairly large number of very, very, very tiny particles.
Right.
So the amount of material measured in grams is very small.
Right. But they did get something, so you can call that a success, and so that was the first, a successful sample return from an asteroid, which is pretty crazy.
Right.
And so hopefully this time, in Hayabusa 2, they will do even better.
The OSIRIS-REx, which we mentioned, and the party that Anna crashed. So I guess you don't want to tell us whose party it was.
I actually don't know.
Okay. You just crashing the party.
That's the hallmark of a good party crash.
Who knows whose
remember.
party it is?
Yeah. Mm-hmm.
Yeah.
Just wandering down the road, seeing an awesome party.
Where was it?
It was at a timeshare that was out like by the Cape. So
yeah. This sounds pretty sketchy to me. Who are you with? Some friends whose names you don't really want to say, and you're just like crashing to some timeshare at the beach.
Yeah.
Yeah.
Mm-hmm.
This really didn't have anything to do with OSIRIS-REx or UCF or space or anything, did it? Okay, I'll take that as your answer. I'm just teasing.
I'm going to plead the fifth.
Yeah. So OSIRIS-REx is doing its sample retrieval with that puff of gas technique. It's got some instrument.
Okay. Maybe Hayabusa wasn't doing that. What does Hayabusa do?
Hayabusa 1, I'm not sure how it did it, but it's a reasonable technique. You don't know ahead of time when you're building the spacecraft what kind of surface you're going to encounter. Mm-hmm. In this one, they maybe know a little bit better because they're actually making an impact crater, and then they're going to go to that. So they're like, no, we're going to smack something into it, and then we're going to go down there. So some reasonable expectation that they're not just going to hit a clean shelf of solid asteroid rock.
Right.
Also, this asteroid, one of the interesting things about this mission and the asteroid Ryugu'd is a C-type asteroid, which is a carbonaceous for carbonaceous. It's a more primitive, we call it, type of asteroid. So it's got more volatile molecules in it than S-type, which are sort of more stony and more metallic asteroids. So this has got organic molecules and more water. Mm-hmm. It's more crumbly.
Right.
I think of it as more cake-like.
Definitely. And you could see from the early pictures of it that its surface it's not some sheet of rock or something like that. It's definitely covered in a layer of soft regolith. And so they should be able to grab some of that.
Yeah. And it's, it looks like your sort of standard kind of, it's kind of conceited to say, it's your standard rubble pile asteroid. They're a dime a dozen. They probably are, but it's kind of new that we've been able to see these things up close from these spacecraft.
Cool. Now, these things are all super far away, right? And they take a long time to get the data back. How long is this?
It is not at the same kind of distance from the Earth that, say, Jupiter or Saturn is. It's closer than Mars. It depends on whether or not the Earth and the asteroid are on the same side of the sun or not. So you can actually get a very big difference in how long it takes for the communication. So actually coming up this winter in the December timeframe, there will be a couple of months where we won't have any contact with the spacecraft because it and the asteroid are going to be on the opposite side of the sun as the Earth. And so that sun, our sponsor, we love you, sun.
Except stop messing with our communications.
We'll be messing with our radio communications. So we won't have communications then. The light travel time from the sun to the Earth is... for some reason, I'm taking the non-astronomer, non-scientist in the room, and I'm peppering her with astronomy trivia questions.
I mean, it's a number question, so I feel like I should go second on that one.
Fair enough. Jim knows.
8 minutes
And
from
change.
Earth to the sun.
Yeah.
Yeah.
I'm going to go 8 minutes and 1 second.
You win. You're closer.
You're closer. Yeah.
Yes. So it takes 8 minutes for light to get from Earth to the sun. So to cross the entire orbit of the Earth is 16 minutes. So if the asteroid is like out, it's a little bit further from the sun than the Earth. So maybe if we're lined up, it's a few minutes from Earth to the spacecraft. If we're on the opposite side and the sun weren't in the way, it'd be more like 20 minutes. So a few minutes to 10 or 15 or 20 minutes, depending on where the two things are in their orbits around the sun. It means that you can't really fly it like with a joystick, but it's not so long that you can't respond to a problem reasonably quickly. Mm-hmm. We talked about the Pluto mission not too long ago, and they had a little bit of an emergency just a week or two before arrival at Pluto. And way out there, it's hours light travel time, and that means the round trip time is twice as many hours. I can do that math in my head. And so then you've got a real problem, because it's like you decide to do something, it's 8 hours before you know whether or not that did something.
Right.
That's a third of a day, and you've only got 2 or 3 days. Yeah. It's not like that with communications with the asteroid or Mars, but you want to kind of like pre-program some things, let it go, do some stuff. Then you wait and you see, oh, that worked okay. Then here's the next thing. You can do all that sort of on the minutes or hours time scale.
Yeah. So. And if it works, of course, it's going to bring stuff back. And I think it's scheduled to return in 2020.
Yes.
Which is not
so far away.
No, not so far away.
Yeah. It is, doing proximity operations at Ryugu'd for the next year and a half, a little bit shy of that. So it'll be studying it, making a lot of measurements, a lot of pictures, drops this impactor, makes the crater, goes get some stuff, then sends that thing back to the Earth on a sort of direct trajectory. A smaller piece of the overall spacecraft comes back. Mm-hmm. So it's pretty amazing that we can do that. And, they're hopefully, and assuming this is successful, JAXA will have done a lot to sort of advance, okay, here you can go explore things and actually bring them to your Earth lab without actually having to send a whole, crew there, or really all of your laboratory stuff there, and do all that operation remotely. So that's pretty cool.
Tremendously important. Because, astronomy is a very difficult science, right? Because you're very often restricted to observing, passively observing things. And so when you can get a chance to do laboratory science where you can do controlled environment and so forth, that's great. So going out and getting stuff is awesome. Usually it's just meteorites that we can do that for. But now we can grab chunks of stuff from anywhere we want. Not quite, but we're getting there.
So, Hayabusa 2 is within a few kilometers already of the asteroid. It's essentially there. So, keep your eye out. We'll be posting some images, and, I'm sure there'll be more, amazing images to come over the course of the mission. It'd be very cool to see this crater that it makes on the surface, see how much stuff it gets back. So it's fun to look forward to. When we mentioned Osiris-Rex gets to its asteroid in just a few months.
Ooh.
So Ryugu'd and Bennu we'll ask you that question again after we've had a chance to see Bennu.
Yeah, we have to check out Bennu.
As more than one pixel. Maybe you'll see if we like it better. Trivia this week is, we're turning the tables, brought to you by Top Quark Jim Cooney. Hence, the trivia is topical. Jim, what have you got for us?
All right. So it's only remotely connected to the things we're talking about today. The thing we're going to talk about after the trivia is the James Webb Space Telescope. And we're going to talk about it just because NASA recently announced, like I said, what's the word?
A new launch date.
Yeah, a new launch date and more money. But in any event,
we're going to talk about why it's still such an awesome thing to do.
Yes, we're going to talk about the awesome things about James Webb Space, because we've mentioned it many times on the program. I don't think we've talked about what it really is and what it's going to do and why it's important. So we'll do that. But I'll mention right now the place where it's going to live is this place in the solar system called L2, which is a Lagrange point. And who cares what that is for right now? Well, you care, you know, Josh? Or you care?
I care.
You care. Okay. Well, we'll get
I'm afraid to say I know. You have a look in your eye like you're going to nail me.
I'm going to nail you. If you get it wrong, don't get it wrong. I bet you know, though. You know your orbital stuff pretty well. So the Lagrange point is named after
Lagrange. Yes, I got it.
That's not
Sorry,
the trivia
Anna.
question.
Come on, man.
So the point's namesake is Joseph Louis Lagrange. He was a very bright Italian mathematician and astronomer. And in 1766, he became the director of mathematics at the Prussian Academy of Sciences in Berlin, where you were just
last week.
Just last week for a meeting of the Cassini group.
We mentioned Cassini a lot.
Yeah. So your question is a historical one, actually.
Okay.
What other very famous mathematician did he succeed in that role?
Okay, name the title again.
The title was the Director of Mathematics at the Prussian Academy of Sciences in Berlin.
And he came after somebody.
He came after somebody. In 1766, he was named to that post, and he succeeded another very famous
mathematician. Okay, I can tell Anna knows the answer, but Anna, don't blurt it out. Okay?
Don't blurt it out. No,
we're going to come back.
Hang on to it.
We're going to come
back.
Let
our
to
listeners
the
think about it,
yeah.
And then there's a secondary.
There's a bonus trivia?
There's a bonus trivia after that trivia.
Okay,
but,
is the bonus trivia easier than that
No,
one?
the bonus trivia is harder.
And the first one you're not giving multiple choice? That's definitely one that should be multiple choice.
Really?
I was
You
thinking
think
that
so?
myself.
It should totally be
Reduce
multiple
cognitive
choice.
load.
Yes, take it from the cognitive specialist here.
Okay.
I would have made that a multiple choice, Jim.
Okay.
I'm just saying.
All right, fair. Maybe in the few minutes between then and now, I'll
You're
think
going
of
to
a few
pick
choices.
up some choices. Okay. Yogi Bear, Scooby Doo.
Yeah.
Okay. So speaking of JWST.
JWST. So this is the James Webb Space Telescope.
Now slated for launch in March of 2021.
March of 2021. So this is, the kind of successor to the Hubble Space Telescope. Hubble Space Telescope has been a marvelously successful telescope. I can't remember when that was launched. 1980 something.
Around 90.
Around 1990. Yeah. But it's been up there for a very long time. It has taken a huge number of tremendous pictures, and we've gotten a huge amount of data from that. But it's on its kind of last legs, right? So we've done the last fix-up mission that we were going to do for the Hubble Space Telescope when it dies next time because its batteries die or whatever.
Gyros or
whatever breaks down on it, it's not getting fixed this time. So we need a successor. So the successor has been the James Webb, or is going to be the James Webb Space Telescope. It's been a tough road for the James Webb Space Telescope.
It has. It's long over its original schedule for launch. And you mentioned that Hubble, we can't service it anymore. We used to service it with space shuttle missions. Astronauts go up there, put new instruments in, they'd replace failing components. You could do sort of like a new science investigator. This is what we do with ground-based telescopes.
Right.
The telescope is, a big light collector and some optics, and you can put a spectrometer at the back or an infrared camera or a visible light camera or whatever. Yeah. And you get a better camera. You can go plop that on the back of a telescope. So we did that with Hubble. Of
course, it was way harder for Hubble than it was for ground-based telescopes because it's in space. But
that's right.
It was in near-Earth orbit, right? So it was orbiting just above the surface of the Earth, so you could get there very easily. Not very easily, but as far as space
just
stuff
have to
goes,
launch a rocket with some people in it.
Launch the space shuttle with some people in it, and you could rendezvous with it. And it was built to have its stuff replaced, right? So you could just unscrew things and whatever, and unbolt them, and take old stuff out and put new stuff in.
On the other hand, JWST will never be serviced.
It will not be serviced.
Maybe one reason why there have been, such delays and overruns is because they know this is it.
Yes. Once you have to get it right
once
the first
that thing is up there, that's it.
Yeah.
There's no fixing.
Yeah, you gotta be really, famously, the Hubble Space Telescope, when they first sent it up there and turned it on, all the images were fuzzy because there was an aberration in it didn't focus correctly.
Yeah.
So they had to spend a huge amount of time and effort going back up there to fix it. If that happens with James Webb, that's
screwed.
It. That's just $10 billion down the drain.
Right.
So get it right.
Yes.
Which is what they're doing. But of course, that means a lot of money, a lot of testing.
Right.
I think it originally was supposed to be a lot less expensive, right? It was originally supposed to launch in, 2011 or something like that on a $1.5 billion-ish budget.
Yeah.
Of course, 2011 has come and gone, and now it's 2021.
Those were the days.
The good old days.
The good old days.
But now the budget is pushing something like $9.7 billion and 2021. But all of the NASA people and scientists keep saying, okay, that's a lot of money. We'll give you that. But it's worth it.
And, so why? James Webb, it's not, so obviously it is not just Hubble.
No,
In
it is
fact,
not. It's not just
like,
Hubble.
It's
Redux.
not really Hubble at all.
No,
except that it's a big telescope in space.
it's a big telescope in space. So a few things that make it different from Hubble. First of all, it's a much larger telescope. So Hubble's main mirror is about 2.4 meters across, which, by the way, as far as Earth telescopes, would not be very big. We have Earth telescopes that are 10 meters across, but Earth telescopes suffer from the fact that they're in Earth's atmosphere, and that screws everything up. So a 2.4 meter telescope, 2.4 meters means the diameter of the mirror on the telescope is 2.4 meters. In space is way better than a 10 meter telescope on Earth for most purposes. And
Anna, do you know? It's just
yeah,
irresistible
I know.
to pick
You got
on
another
you.
person here. You got
It's
to
irresistible to pick. Irresistible to
I'm
pick
going to
on
go
you.
with no.
Do you know why the Hubble mirror wasn't bigger, like twice bigger? This is a completely trick question.
It is a trick question.
Was it like a mistake or something?
No. Just
Would
like
it not fit?
it wouldn't fit.
That's it.
That's right.
Okay.
You got it
Yeah.
right again. You're on a roll.
Oh,
You're
I
on
was
a
going to
roll.
go with it
It
didn't
wouldn't
fit,
fit.
but then you were
But
like,
why
it's
not?
a trick.
Well, so really what I'm trying to get to is a fun sort of game that probably all our listeners are familiar with in some sense. It's like, why are rockets the size that they are? Why wouldn't you make something that's bigger so you could fit a bigger mirror in it? The bigger mirrors are better than going all the trouble to send a mirror up into space. So why are rockets about the size that they are? And this is a little bit of a BS answer now because of the way things are developing, but
because you can just strap a few of them together and then
you have to build your rocket on the ground. And you have to get it from where you build it to where you launch it, and that means it goes on railroads and through railroad tunnels, and those are a certain size.
And the crawlers.
And the crawlers can be
for
huge.
the-
Those can-
That's
yeah,
just
those are
going.
huge.
That's just going a couple
Okay.
miles on the Cape. But it's sort of cross-country transportation
Oh.
for the shuttle boosters was set by railroad transportation. And what determines how big railroads are is historically, this is all whatever. This is tangent of tangent, but it's a fun story.
I'm going to ask follow-up
It just has to
questions,
do
so.
with roads. What were original roads? Original roads were first people, then people on horses, and horses side by side. And so it's twice the width of a horse's ass. So that's what set
Interesting.
how big ultimately the Hubble Space Telescope mirror is.
That's amazing.
Because it couldn't be collapsed any small, like it couldn't be put together in pieces. Is
So you
that
could do that, and
So that's exactly what we're doing with the James Webb Space Telescope.
Ta-da.
So the Hubble Space Telescope mirror
I
is
meant
one
that.
the awesome
piece.
segue.
Yes,
Way to
beautiful.
segue us
Excellent
back.
job. Yes. That's just the thing. So if you want to make it bigger than about 2.4 meters, you have to build it in pieces. And so the James Webb Space Telescope will, in the end, be about a 6.5 meter diameter telescope, but made up of something like 18 individual smaller mirrors built into like an array that makes it appear as if it's a one much larger telescope. So that's awesome. That allows you to fit it inside of the rocket that will launch it. Unfortunately, that means that when you get to where it's going to be and deploy it, it has to kind of automatically deploy itself into the proper array, this bigger array of things. And it has to all work, right? If it doesn't, if all the pieces don't lock into the right place once you get there, then the whole mission is scrubbed. Not scrubbed, but is worthless. So it's a challenge to build a thing that is really big that will unfurl itself once it gets there and have it all work properly. And that's a lot of what they're testing, they're doing now is testing these systems where it's not just actually even the mirror that has to unfurl, it's the
shade.
sun shield, right? So yeah, it's going to be out there.
So this is really the big difference between JWST and Hubble.
Right. So one of the
Isn't
differences
that-
is how big it is. The other difference is what kind of
light.
wavelengths it's going to look at. So this is more of an infrared telescope than an optical telescope. And that presents its own challenges because things like spacecraft emit infrared light. So the Hubble Space Telescope, for example, emits its own radiation because it's not cold. It's near enough to the Earth and Sun that it's warm-ish, and so it lets off infrared light. So does the Earth. So does the Sun, right? So what you have to do, if you want an infrared telescope, which is what James Webb is supposed to do, and I'll tell you why in just a minute, is you have to make it very, very cold. And one thing to do to make it very cold is block all the sunlight that's going to get to it. So you have to have a big giant shield that blocks the sunlight and the Earth light.
Also why it's off at L2.
Right. L2 is this point in the solar system that's beyond Earth. So it's orbiting the sun, not orbiting the Earth, but it's out beyond Earth's orbit. So it's far away from the Earth and even farther away from the sun. which means you build a sun shield, but that also turns out to be an Earth shield because Earth and Sun are both in a line compared to, so it blocks out all the light from all that stuff, which allows you to keep the instrument or the whole thing very, very cold, which means that it itself does not emit very much infrared radiation, which means that you can see infrared radiation coming from the stars and galaxies and stuff that you want. So, yet another challenge. And I think that one of the things that happened with this most recent batch of testing was they unfurled that sun shield and it tore as it was unfurling, and that's bad news.
That's
so
bad.
They have to fix that.
Testing is important. This is a lesson that we know, but building our own little CubeSats are tiny, tiny little satellites in comparison to JWST in every sense of the word, in terms of the scope of the mission, the budget, the timeline, physical size, size of a box of Kleenex or little satellite we're building. Boy, I wish we had more time for testing.
Yeah. It's kind of cool. I mean, you and Eddie build spacecraft. It's kind of like the amount of frustration and time and effort and manpower, person power that has gone into making those little tiny things that are in scope so small compared to James Webb gives you an idea of like what kind of a pain in the butt building a grand scale.
Right. So tell us
instrument.
about the awesome things you do in the infrared. Why are we looking in the infrared?
Yes, why are we looking in the infrared? Well, there's a couple good reasons to look in the infrared. One, it's very hard to do that from Earth's surface because infrared light, some wavelengths of infrared light don't penetrate the Earth's atmosphere at all or very well. Other wavelengths of infrared light, are absorbed by water and other things in the Earth's atmosphere. So the Earth's atmosphere sucks for viewing a lot of infrared light. So you need a space telescope. And a lot of the things that we're interested in looking at emit lots of infrared light, like stars and galaxies in the very, very, very early universe.
Right, because infrared is redder than the red light that we can see with our eyes.
That's right.
Mm-hmm.
And that means longer wavelength. And back in, if we're looking at distant things, there's more, what's the cosmological redshift?
Yeah.
Is that the term?
Yeah.
Due to the expansion of the universe, things that are very far away from us are stretching away faster, and therefore the wavelengths of light actually stretch. So things that would be visible light, if they were in the room with us now, are stretched out into infrared if we're looking at them back in the early universe.
That's right. Exactly right. So we're looking, one of the things that probably the main thing that James Webb was designed to do was see the very first stars and very first galaxies in the early universe, using the infrared. But it's also going to be able to see anything else that gives off a fair amount of infrared light, like planets, for example, give off a lot of infrared light. So this you may be able to directly image
what about
planets around other stars.
Aliens?
Space aliens. Absolutely. They give off infrared light.
In Solo, there was a giant space octopus. Did you see Solo, Anna?
I did not.
You did not.
You're not a Star Wars person?
I'm not a Star Wars person.
Star Trek?
Yes.
All right.
Definitely a Star Trek person.
Explain why Star Trek is better than Star Wars.
Oh, we don't have enough time.
I know, right?
Not enough.
Bullet point it.
Isn't it obvious?
It's not obvious. When I poll my classes, 90 to 95% of them say the Star Wars franchise is better than the Star Trek franchise.
And 85% of them say that the summer is because the Earth is closer to the sun.
I know, but it's not obvious why that's true, and it's not obvious why Star Trek is better. Right. But it's not obvious why it's not true unless you know something about scales. It's not going to be obvious why Star Trek is better unless you know something deep about
Here's why.
Sci-fi.
Okay. So I'll say something, and Anna might want to. Do you want to?
No, go ahead.
Okay. Star Trek, first, it's about us. It's about people. It's about the future of our own society and our own civilization, rather than some far off galaxy a long time ago in a galaxy far, far away and aliens that aren't us. So it's about our own future, and it's a very optimistic, hopeful vision of the future. And the original version of Star Trek is, here is how we can become better, and here is what a better version of ourselves looks like. And it is a struggle to get there. In the best episodes of Star Trek, they are struggling mightily to be better than they were and better than we are, and they frequently achieve that progress forward. And so it gives us a beacon of hope and light for the future of humanity.
Oh, well said, Josh.
That was well said.
Well said. What about you? What about you?
I also feel like Star Wars is more, focused on like the battle aspects of things. Mm-hmm. And I feel that there's so much depth in any of the Star Trek series. it's also personal for me. So I grew up watching the Next Generation.
Yes.
And I actually have a picture of the Enterprise in my office. And like Data was just one of my favorites ever.
I should get some kind of Star Trek stuff in my office.
A few more. Yeah. And also since I'm a social scientist, from a social science perspective, like there's just so much there that you can look at. Like one of my favorite things is the dynamics between, in an original series, is the dynamics between, Spock and Kirk, and how we the way that the series is framed kind of puts Kirk almost up on a pedestal. Even though Spock is always there to have like the rational counterpoint, we kind of still romanticize this idea of just going and doing a thing and it'll work out, even though I'm a Spock person all the way. But I have my science officer dress at home. But
Awesome.
Yeah.
Awesome.
So yeah. So I mean that's just one of the things, but there's so much to it. And I mean, it's a series too, versus.
Yeah, in fairness, there's more Star Trek.
There is more Star Trek.
And also more Star Trek to hate than Star Wars.
There is. Although there's a lot more Star Wars than just the 10 movies or something. There's also
there's games and books and all that
videos
stuff. And of course, they're not trying to do the same thing. So, they didn't ask to be compared, and I like them both. And I also sometimes hate them both. There are pieces of Star Trek I can't stand. There are pieces of Star Wars I can't stand. And there are pieces of both that I love. Anyway, tell us the answer to the trivia.
Oh, do you want some choices?
Sure. Did you think of some choices?
I could come up with some choices.
On the fly. That's pretty good.
That's going to be very challenging.
Okay.
But, how about, one option is Copernicus.
Okay.
One option is Pascal.
Okay.
One option is Gauss.
Uh-huh.
And one option is Euler.
Okay. You probably wouldn't believe this, and unless it turns out to be wrong, in which case you will believe it. But my original guess was going to be Gauss.
Was going to be Gauss? Okay. Yeah. Anna?
Oh my gosh.
You did get to go second.
I'm going to go with Pascal.
Fascinating. I'm gonna give myself props for coming up with good, awesome choices on the fly.
It's Euler.
The real answer is Euler. Euler. Leonard Euler.
Yeah.
And the follow-up question is, so Leonard Euler, he was much like, Lagrange was kind of a jack of all trades, did a lot of things, did a lot of cool astronomy things and cool math things and cool physics things and whatnot. But, in my mind, Euler is most famous, or the thing that he did that I love the most is his identity, Euler's identity. And
I don't know that.
You do know Euler's identity. You might not know that it's named Euler's
Leonard
identity.
Euler. That's his identity.
That is.
He was the imperial mathematician in Prussia before Lagrange.
There you go.
I do know his identity.
That is his identity. Mathematical identity. And I don't know. I'd be interested to see. This is the thing. I know you know this.
This is a highly nerdy
thing. We're going into math. Usually we're talking, but math can be a beautiful thing, right? Math is often taught as this very boring thing to memorize. But anyway.
I love math.
We're going to see if you have seen this before or not. And
okay.
the Euler's identity, I don't even have to write it down. It's easy enough. It's got only a few things in it, right? E, which is what? About 2.7 something. It's the base of the natural logs. Little e is, in mathematics here. It's just 2.7 something. It's one of these irrational numbers that goes on forever, but 2.7 something.
Yeah.
If you raise that to the power of pi times I. And what is I?
Square root of -1.
I is the square root of -1, which is
imaginary.
It doesn't exist. It's called imaginary because it doesn't exist. There is no thing that is the square root of -1.
Only in my dreams.
So we just call it I. So if you take E and raise it to the power of I times pi.
Yeah.
And plus 1 to all that, you get 0.
Yeah, that's crazy.
And I know, write that down, good listeners, because that means to me that I've been doing math for a very, very long time. And I can prove that, right, with theorems, whatever. It still doesn't make any sense to me. E is like 2.7 something. Pi is like 3.14 something, right? You can't take something, 2.7, raise it to a power that doesn't exist because you took 3 point something multiplied by I, which doesn't exist, and get -1. But you do.
You might say it seems irrational.
Oh.
It does seem irrational. But that's Euler's identity, and it's true.
What's the bonus trivia?
That was the bonus trivia. I don't know. It was. I was gonna.
I had to say what it was equal to.
whether you knew that identity or not. Which I know you know the identity,
I have seen
but you don't.
But I wouldn't
have known
it.
that it was called Euler's identity. Anyway, have you seen that, Anna, before?
I have not.
You have not. Yeah. Well, that should haunt your nightmares.
Well,
for
that
weeks.
$3.95 will get you a medium latte at Starbucks. Well, even though you've been stuck in a traffic jam this whole time, it was actually a Walkabout the Galaxy in our imagination.
Yes.
Be sure to like us on Facebook to get all our updates, and check out our website at walkaboutthegalaxy.com, where you can also see some of our past sponsors. Follow us on Twitter
at walk_the_galaxy,
where you can ask us questions and suggest topics that you'd like to hear us discuss. Our theme music was composed by Richard Jerusik. Catch up on old episodes wherever you get your podcasts, and write us a review in the sand of Waikiki Beach in Honolulu. Take a picture of it and tweet it to the world. I'm Josh Caldwell.
And I'm Jim Cooney.
Thanks to Anna Turner for joining us today. We're some of the Astroquarks, signing off until the next episode of Walkabout the Galaxy.